Good day, everyone. Today we'll be having another example on lateral earth pressure. In this example, we need to determine the Rankin's active force per unit length of the given wall below and the location of its resultant. So we are given a retaining structure or retaining wall with a height or a depth of 6 meters, and the backfill soil is sand having a dry unit weight of 16.5 and a saturated unit weight of 19.2 kilonewton per cubic meter. There is a groundwater table found at a depth of 1.2 meters below the ground surface. And with this condition, an angular friction, effective angular friction at the or above the groundwater table is 30 degrees, and below the groundwater table we have 35 degrees. The cohesion is 0 because we're given a sand soil. In order for us to determine the Rankin's active force, it is better to draw the pressure distribution and calculate the active force per unit length from the pressure distribution. And for us to draw the pressure distribution, we have to calculate the active pressure for both soil and water. Let me just prepare the figure before we start drawing. And it's not. Okay, let us just say that this will be the preparation for the pressure distribution for the soil and for the water. And since the soil is sand, there is no effect of cohesion or no cohesion at all, so we will not consider cohesion in the analysis. But the first thing to do is to solve first for the Rankin's active earth pressure coefficient, or K sub A, and we have two layers here, the one above the groundwater table and below the groundwater table. So let us say for the upper layer, our K sub A, let's say this is 1, that will be equal to 1. Our formula is 1 minus sine of phi prime divided by 1 plus sine of p prime. And we have 1 minus sine of 30 degrees over 1 plus sine of 30 degrees. And this is 1 over 3. Then we solve for the lower layer, and that is below the groundwater surface. And let us write this is K sub A2. Having the same formula, we have 1 minus sine, but this time our angle of friction is 35 degrees divided by 1 plus sine 35 degrees. And we have here 0.271. Okay, after solving the K, we can now solve for the active pressure for every layer so that we can draw the pressure diagram. So let's consider for soil. Let us say at H or Z, you may want to consider H or Z as the height. Our active, sorry, is equal to 0, so because there's no pressure yet. Then at, say, H is equal to 1.2 meters. And since we have a groundwater table, we have to consider the upper portion and the lower portion of the groundwater table. So let me just say this is 1.2 meter. Let me write just above the groundwater table. Our pressure is equal to Ka1 multiplied by, of course, the sigma O, or the effective stress at a depth 1.2 meters. That would be equal to, where Ka1 is 1/3 multiplied by the dry unit weight of 16.5 and multiplied by the height of 1.2 meters. Okay, so from here, the answer is 6.6 kilonewton per square meter. So if you want to plot that one, we started from 0, it then increased to a depth, or a pressure of 6.6. Okay, that is the pressure, active earth pressure at the depth of 1.2, just above. But then at the intersection of the ground of layer 1 and layer 2, so let us write at H equals 1.2 meters again. Let me write just below. This is equal to, our formula is this time using the pressure coefficient at 2 multiplied by sigma naught prime, and that is equal to, we have 0.271 multiplied by 16.5 again, and 1.2 meters. And this will give us 5.37. Okay, so going back to the pressure distribution, we have to record the 5.37, so this portion. Then we have, let me just write it in here. At Z, or sorry, I'm using H. At H equals 6 meters, then our active pressure there would be our K sub A2 multiplied again by sigma O prime at the depth of 6 meters. And that would be equal to our K sub A2 of 0.271 multiplied by, okay, from the top we have 1.2 multiplied by 16.5 plus, we have 6 minus 1.2, that will be 4.8 multiplied by our submerged unit weight, and we have saturated unit weight of 19.2, and we need submerged, so we have to subtract the unit weight of water, right? Then that's it. So we can solve for the active pressure coefficient at the depth of 6 meters, and that would be equal to 17.58 kilonewton per square meter. So if we're going to plot that here in our pressure diagram, this is 6.6. Let me just place it here. And then, okay, sorry. Let us say this is our 17.58. Okay, then aside from that, we have to consider the earth pressure or the pressure coming from our water, or for the pore pressure. Let me write here for the pore pressure. We have at H is equal to 0. Our pore pressure is also equal to 0. Then at H equals 1.2, our pore pressure would still be 0. So this will just be simply a straight line. Okay, so it's still 0. Then at H equals 6 meters, our pore pressure becomes, okay, we have 4.8 multiplied by, of course, gamma W, and this would be equal to 4.8 times 9.81, and this becomes 47.1 kilonewton per square meter. So we have here let us say this is 47.1. All right. So again, this is our U, and this is our sigma sub A prime. Now that we already have the pressure diagram, we can actually locate or get the pressure, force, or the active force, and we can divide this into two sections. And we have here the pressures located at the centroid. Okay, so let us say this is P sub 1, P sub 2, P sub 3, and P sub 4. So to get the total force acting on the retaining structure, let's say this is the total active pressure, or the total active force. We have P active. We have P sub 1 plus P sub 2 plus P sub 3 plus P sub 4. Okay, let us now plug in values. P sub 1 will be triangular, and we have a base of 6.6 and a height of 1.2. So this becomes 1/2 of base of 6.6 times 1.2 plus our P2 is triangle. We have 5.37 and 4.8. So we have a base of 5.37 and a height of 4.8. Then for the triangular P3, we have a base of, we have to subtract 17.8 or 58 rather by 5.37, and we have 12.21 as the base of this triangle. So this is 12.21. So we have 1/2 of the base, 12.21, multiplied by a height of 4.8. Then we also have a plus our water or pore water pressure. We have triangle 1/2 having a base of 47.1 and a height of 4.8. Therefore, calculating this term, we can get a total active force of 172.08 kilonewton per meter. Okay. And lastly, if you want to get the location of the resultant, you simply take the moment about the bottom of the wall and take a moment at the bottom of the wall here, some moment, then we'll be having the following. So we have, let's say this is y1, and this is y2, and this is y3, and which is equal to our y4. Okay, so to get the location, let's say this is y bar, that is equal to p1 we have our total force, we have PA multiplied by y bar, which is equal to P1 times y1 plus P2 times y2 plus P3 times y3, and we have plus P4 times y sub 4. And so to solve for y bar, we have, you can just substitute or plug in all the values. We have not calculated here, but P1 or y bar can be calculated as 1.8 meters. Thank you.